Molecules can have many different shapes. Even simple molecules with 3 atoms can be linear or bent. More complex molecules can have various other shapes. How can we understand the shapes of molecules? VSEPR, or valence shell electron pair repulsion theory, will allow us to predict these shapes. The most important concept is the bond angle. For 2 atoms connected to a central atom, the bond angle can vary from 0 degrees to 180 degrees. Here are examples of 3 molecules, all with very different bond angles. How can we understand these differences? To use VSEPR theory, count the number of bonded atoms and lone pairs. The total is the steric number. The steric number allows us to predict the shape of a molecule. Consider BeH2. In the best dot structure, BeH2 has only 2 hydrogen atoms bonded to the central beryllium atom. 2 bonded atoms and no lone pairs imply a steric number of 2. Consider these 2 atoms to be on the surface of an imaginary sphere. The hydrogen atoms, each bonded to beryllium, wish to avoid each other as much as possible. Thus, the 2 atoms will produce a linear shape. Now consider GeF2. This molecule has, in its best dot structure, 2 bonded atoms, but also, unlike BeH2, possesses 1 lone pair. The steric number is 3. Consider 3 objects repelling each other on the surface of an imaginary sphere. These objects will adopt 120-degree angles, and the molecular shape will be bent. Water, H2O, has a steric number of 4. The 4 groups will repel each other to produce a bent shape. In the ideal arrangement, these groups would each define a bond angle of 109.5 degrees. In reality, the lone pairs push on the bond pairs, producing an actual bond angle of 104.5 degrees. XeF2 also has 2 atoms bonded to the central atom, but the central xenon atom has more than 8 shared electrons. VSEPR theory still applies, and the steric number is 5. Repulsion of these 5 objects will produce a trigonal bipyramidal arrangement. The lone pairs occupy the more spacious equatorial positions, forcing the bonded atoms to the axial positions. This produces a linear shape with a bond angle of 180 degrees. These examples illustrate how the steric number guides chemists' predictions of the shapes of molecules. We now proceed to consider molecules with 3 atoms bonded to a central atom. Consider BH3 boron trihydride. Although this molecule has no octet around boron, the best bonding structure has a central boron atom and 3 bonded hydrogen atoms. These 3 bonds will repel on the surface of an imaginary sphere. 3 bonded atoms and no lone pairs produce a steric number of 3. The molecular shape is named trigonal planar, and the bond angles are all 120 degrees. The molecular formula for ammonia is NH3. There are 4 objects in ammonia that will repel each other: 3 bonded atoms and 1 lone pair. Repulsion between these 4 objects will produce tetrahedral angles of 109.5 degrees. This produces a shape called trigonal pyramidal. ClF3 is a molecule with more than 8 electrons around the central atom. There are 3 bonded atoms and 2 lone pairs, so the steric number is 5. This will produce a trigonal bipyramidal arrangement in which the lone pairs occupy the equatorial positions. This forces the atoms to be 90 degrees apart from each other, so the molecule is T-shaped. We have now seen how the steric number predicts the shapes of molecules with 3 atoms bonded to the central atom. VSEPR also applies to molecules with 4 atoms bonded to the central atom. CH4, methane, has a steric number of 4. The 4 hydrogen atoms repel each other equally and yield a tetrahedral shape with a bond angle of 109.5 degrees. SF4 has 10 electrons around the sulfur. The 4 bonded atoms and 1 lone pair produce a trigonal bipyramidal arrangement. The lone pair resides in the equatorial position, not the axial position. This produces 2 different bond angles in the molecule, one of 90 degrees and one of 120 degrees, to give the molecule a seesaw shape. XeF4 has 4 bonded atoms and 2 lone pairs. This produces a square planar shape in which the lone pairs are opposite to each other. The bond angles thus all equal 90 degrees. The shapes of molecules with 4 atoms bonded to the central one are also explained by VSEPR theory. We now consider molecules with 5 atoms bonded to the central atom. PF5 is a molecule with no lone pairs and 5 bonded atoms. This produces a trigonal bipyramidal shape, which has 3 atoms with 120-degree angles in the equatorial plane, and 2 others at right angles from these. In contrast, BRF5 has 5 bonded atoms and 1 lone pair for a steric number of 6. This produces an octahedral arrangement, where every angle is 90 degrees. This molecular shape is square pyramidal. SF6 is an example of a steric number of 6. There are 6 bonded atoms and no lone pairs. All of the atoms repel each other equally, producing an octahedral shape in which every bond angle is 90 degrees. VSEPR also applies to molecules like CO2 that have double bonds. Carbon dioxide has 2 bonded atoms and no lone pairs. The steric number of 2 thus produces a linear shape. Formaldehyde, CH2O, has 2 single bonds and 1 double bond. The steric number of 3 predicts a trigonal planar shape. The double bond, however, acts similarly to a lone pair, repelling the bond pairs and decreasing the ideal 120 bond angle to an actual bond angle of 116 degrees. For molecules with single or multiple bonds, for atoms with and without octets, VSEPR theory provides a simple, useful method to understand the shapes of molecules. Caltech presents the Chemistry Animation Project, using computer animation to visualize the chemical world.